Right. Welcome and thank you everyone for joining us today. If you are new to our Science Speakers webinar series, we're glad you made it. We've invited some of our users that employ remote sensing-based techniques and research that may inspire new ideas or even supplement any project changes others have experienced due to the coronavirus. So our summer speakers were a great success. So thank you for all those that attended. And it's our great privilege to continue our series with our collaborator and super user, Dr. Chunli Dai. First off, my name is Kathleen Torres-Parisian. I'm a PGC User Services staff member, but I also lead PGC's educational and outreach efforts such as this. So before we get started, I wanted to share with you some details about viewing the webinar in Zoom. All participants are muted throughout the webinar. We will have time at the end of Chunli's presentation for a Q&A. Feel free to submit your questions in the Q&A tab. So we are recording this presentation and we will make it available on our website and YouTube channel as our previous webinar materials. There we go. Before we learn more about Dr. Dai's cutting-edge research, I want to provide a brief introduction on the Polar Geospatial Center. So for those that have attended previous webinars, my apologies, as this is the same spiel, but thankfully I'll be brief. So we are a polar science and logistics support organization at the University of Minnesota. Our core funding is provided by the National Science Foundation's Office of Polar Programs. However, we do receive other funding from additional agencies, including NASA's Cryosphere program. Our mission is to provide domain and institutional knowledge to solve a broad range of polar geospatial problems, to provide access to sub-meter commercial satellite imagery over the poles, and the experience to task, manage, and process imagery and other high-level value-added products. And lastly, to provide educational courses and online materials to transfer our knowledge and experience to the community. So PGC's main products and services that enable our mission to come to light are best described to fall into these four categories: satellite imagery, terrain models, digital maps, and geospatial support. We have access to a lot of high-resolution sub-meter commercial satellite imagery from Digital Globe, enough to cover over 95 Arctics and over 90 Antarctics, basically over 6 times the surface of the Earth. Another major product and service PGC provides are terrain models. So elevation data is central to many science and logistics projects, and we've partnered with other public and private institutions to automatically produce freely available, high-resolution, high-quality digital surface models using the abundant digital globe imagery. So we're thrilled to have Dr. Dai tell us how she's been using ArcticDEM, and for our Antarctic enthusiasts, check out the reference elevation model of Antarctic, or REMA, on our website. So PGC stores and distributes polar geospatial data developed in-house and from external sources. So at PGC, we know maps are important tools, and they're not just pretty wall hangings. We have hundreds of contemporary and historical polar maps searchable online in our map catalog, among other online geospatial databases. If you're curious to learn more, our website provides exhaustive information about PGC. Check it out at pgc.umn.edu. So we have a breadth of users from the general public to Antarctic pilots, to ornithologists, to cooperative agencies. For users like Chunli, our role to scientists is essentially all geared to providing geospatial expertise to enable scientific objectives and hopefully to help users reach them more efficiently and effectively. And we spend our time processing and manipulating data so researchers can spend their time on their cool science. So we are in unprecedented times, and as I previously mentioned, we're taking this opportunity to showcase and connect our users through their research. Our users are leaders in innovative thinking and use remote sensing techniques to reach these far corners of the world in the Arctic or the Antarctic to discover more. So we know their findings can inspire more, and that's why we want to share that. So we are beside ourselves to have Dr. Chunli Dai as a science speaker today, featuring her work and ours, and we look forward to our upcoming guest science speakers, including Dr. Ellen Enderlin from Boise State University next Wednesday at 12 p.m. Central, and Andrew Fleming from the British Antarctic Survey on October 14th at 10 a.m. Central. Please visit our website or social media accounts about registration links and abstracts. So without further ado, I'm excited to welcome our third science speaker guest, Dr. Chunli Dai. Chunli is a senior research assistant at Byrd Polar Climate and Research Center at The Ohio State University. She has been a close collaborator and super user of our elevation products. Chunli's research investigates Earth dynamics and topographic changes from naturally occurring events like earthquakes, volcanic eruptions, and landslides, and uses a variety of traditional and pioneering techniques. She has innovatively utilized the ArcticDEM data to measure lava flows in Kamchatka, to tracking volcanoes and landslides across Alaska. Chunli, thank you for being here and sharing your work with us, our users, our friends, and our followers. I'll let you take it over from here.
Thank you, Kathleen, for your nice introduction. Yes, I'll share my screen from here. Can you see my screen, Kathleen? Okay, great, thanks. Okay, I feel very honored to be here, to be part of this series. And thank you everyone for joining us. Today I'll talk about our recent work on mapping volcanic eruptions and landslides from using ArcticDEM data. So I have been working with ArcticDEM for about 5 years. Before that, I mainly worked on change detection using satellite gravity data. And back then I thought like gravity is very cool, right? There was even a movie called Gravity. So do you know what is the spatial resolution of satellite gravity data? It's more than 100 kilometers. So it's really broad scale. So when I first heard about this ArcticDEM datasets, they can provide 2-meter resolution data, I was like, forget it, gravity, I'm gonna go with DMs. So our project on mapping volcano eruptions and landslides are funded by NASA ESI program. Our team members include Howard from Ohio State University, Jeff from Michigan State, Anna from Woodwell Climate Research Center, and actually I have a lot of collaborators, Anthony from University of Ottawa and Dr. Hickman from Ground Truth Tracking. We are also expanding our collaborators through the progress of this project because so many people are interested in this work that we are doing. So that's very exciting. Here's the outline of today's talk. First, I'll talk about a brief introduction of this project. Then I talk a little bit about the algorithm development. And then I'll show several cases for the volcanic eruptions and several landslides. After that is some challenges and the summary. So for change detection using repeat DMs, the first thing we look at is how many repeat measurements we have. That's critical. A lot of you are probably very familiar with this. Just for you now, for some of you, those that you are not familiar with this, so this colored map shows the data coverage of ArcticDEM and our main study sites. So these red triangles shows the volcanic eruptions during the past decades. So there are several eruptions in Iceland, a lot of them along Aleutian Islands in Alaska, some in Kamchatka. So, and the other symbols show some known landslides, like the 2017 landslides in Western Greenland that actually caused the tsunami and damaged a village nearby. And so some of the other symbols show sites of slums. So we have a lot of known sites of the landslides, but for the majority part of the area, we don't know like where we have landslides. So that's one of the main goal of this project is to automatically detect the natural hazard events. So this map shows you how many repeats we have. Like the red is more than 10 repeats, blue is less measurements. You can see a lot of the areas we have a lot of data, a lot of repeats, and the blue area, some of the part has less measurements. And this figure shows you the time span, like most of them are more than 6 years of data. So that's pretty good. That's good for our project. So this just showing that our project was featured in US News. So I'm very happy that a lot of people are interested in this. This objectives. First is to quantify the volume and extent of volcanic eruptions and landslides. And then our goal is to generate a pan-Arctic mass wasting inventory. Using that inventory, we can analyze the linkage between mass wasting events and climate changes. Before you using repeat DMs for change detection, the first step, very critical, is the precise DM registration. At a certain location, for example, you have two DMs, one measured in time T1 and another DMs measured in time T2. There will be horizontal or vertical offsets between those two DMs that's caused by the errors in imaging sensor models. And then what you do is precisely estimate the offsets between those two DMs and then apply the offsets, align those two DMs together. Recently, our group in Ohio State developed by Ian Howard, that he find a new method to improve the registration by the stacking of different images and DMs, and that works really well. So, for example, you have 4 DMs, A, B, C, D. The traditional way we have been doing is find a reference DM and co-register the rest of the DM to the reference DM. And now what we do is estimate the offsets between all possible pair of DMs. Then you have redundant measurements of the offsets between different DMs. And then you can do least square adjustments that can give you a more precise estimate of the offsets. So in this way, we can get a more accurate registration. After we're done DM registration, then we can try to figure out what's the real topographic changes caused by like natural hazards. This is an example that for a volcano eruption in Tabatek, a volcano. So this figure shows, for example, at one location, you have the surface elevation measurements. Like here, this vertical red line shows the duration of the eruption. And then you can see before the eruption, you have 2 measurements, height measurements. And then after eruption, you have 4 elevation measurements. And then you use simple step function. You can estimate the elevation changes, and pretty simple, right? And then you can also estimate the uncertainties. But sometimes you don't know where the changes occurred. because it's unlike for volcanoes, you know the volcano size, the location, and a lot of the landslides, you don't know where it occurred. And in this way, we have to do, and you don't know when, the time. So in this case, we have to search in a large area. And for each location, for each point, we don't know the time of the change. So we estimate the time of the change. What we do is do differential elevation between sequential measurements. And then for this, for example, here, so majority of the pairs, you get around 0 height change because mostly there will be no changes. And then for this one pixel here, you see a large change. Then between this, that means between these two measurements, there is a change. And then you can estimate the time of the change. So by doing that, we can get a 2D elevation change map like here, this map shows. So you can see some of the areas have larger signals. Some of the areas have around 0 signals. It's interesting, like around in these areas, like have around 0 elevation changes, because we also estimate the time of the change. You can see in this area, the time of the change is kind of random because there's no change, right? So you can't really tell. And then, but for this area, like we know seems to be there is a big change here, and then you can estimate a homogeneous time. Yeah, so in this way, we can both get a map of the magnitude of the change and the map of the time of the change. And then we can do some filtering to get the pixels, a group of neighboring pixels that represent actually an event. So for example, here, what we did, this map is criteria 1 is the elevation change, is the time of the change is homogeneous, is not random. And then criteria 2 is the magnitude of the change is significant, is large magnitude, and uncertainty is small. So then you see here, we got a quite good cluster of the pixels, which actually represent some real changes. And these, so some of these sites here are validated by field measurements, and some of these sites are not. It means that's what we observe from the ArcticDEM data products. That's a new results, right? And so further on, we will apply more steps like to do improve this mask. Like we're using some glacier database as prior information. We can analyze the original imagery to see the land cover changes, and we can use some machine learning algorithm to help us identify those mass wasting events. That's all for the algorithm development. Now is let's go to the application. First one I like to show is this 2001 Cleveland eruption in Alaska, not Cleveland, Ohio. So here's the location. It's along the Aleutian Islands. This is very hot, very popular site. A lot of scientists when they show my presentation at a conference, they come to me like, "Oh, your data set is so cool. Can you see Cleveland?" Okay, so I was like, okay, I'll go back and take a look. And here it is, what we got. This 2D map shows the elevation change. A lot of them areas show 0 changes, which is good. And there's red areas show actual lava, the thickness of the lava. So you can see elevation increase about 30 meters. So that's very cool, right? So this time series here will tell you how many DMs we have. This is pretty early, like 2001, like 20 years ago now. We have one measurement that's SRDM before the eruption, and only like 10 years later, we got one ArcticDEM. and then several more later on. So, but now I don't see any publications in the literature from the mapping of this volcano eruption. So I think that's pretty cool. Like for 20 years, we don't know what happened here, but now we know because of the cool product here. Here is some profiles to show some details. Like here, AA prime profile is across the summit of the caldera, a crater. So the black line is the topography before the eruption, so it's kind of flat here. And then the other colors show eruption, so the topography after the eruption. So you can see the lava flow out from the summit area and then blast off the material out and create a new crater here. So and B prime is along the middle part of the lava flow, and you can see the black line is before eruption and other colors after the eruption. You see the variation of the thickness, so you can see a lot of details. Also, in the bottom of the lava flow, see similar features, like you can see all the details of the variations. So yeah, it's the question we want to try to answer is that why it flow this way, like to the west? Is there any like local, before the eruption, is there any like local low areas of the topography? But we don't see anything like that. So this kind of data can help us understand a lot of these kind of questions. So 3 months ago in June, there was another eruption in the same site. From the satellite imagery, July 1, we kind of see the flow of debris to the east, to the north, a little bit like that. Thanks to Paul, he helped us to request some new imagery in the same site. So here we got a awesome image in August. So it looks very clear, low clouds, and you can see from this image back in June, a lot of snow coverage. Don't worry, there will be an interaction between the hot material from the eruption and the melt of the snow, make things very complicated. But here we have the image in August. You can see it's kind of all the snow has melted. So, and by comparing that with the DMs before, we actually can get a pretty good quantification of the lava flows, not the debris flows. So that's a lot of information we can get using ArcticDEM. And here's another example in Byrd of Iceland. So this volcano is very interesting, like it's very unique because you see the lava flows over here outside of the ice cap, and actually the caldera, where the magma reservoir is located here is in the ice cap, is in a different separate location. So you can see a lot of cool stuff. Like not only you can measure the lava flows, and you can, using the DMs, you can see the ice surface subduction causing by the magma withdrawal during the eruption process. So this study, this volcano eruption actually has been studied by a lot of researchers. Anyhow, ArcticDEM, the benefits is that we see very high resolution, the best 2 meter resolution, right? This is what I got for this area. So the red shows the thickness of the lava flows. It's very pretty cool here. And the here blue here actually represents the surface subduction caused by the magma withdrawal. And besides that, you see a lot of other areas. Like here, you see a lot of blue, some points of blue here and there. Those are actually caused by ice cauldrons, which is caused by the leak of magmatic heat. Actually, our results agree well with some of these results mapped from aircraft-based radar altimetry. from other data sets. So here is a profile along these ice cauldrons in this right figure along AA prime here. So the cyan color shows the elevation before the eruption, the ice surface, and then the other blue and magenta color shows after the eruption. So you actually see the ice cauldron is still progressing after the eruption till 2017. You still see variations like the deepening of the ice cauldron and the progress and the moving of the location. So there are a lot of details that we can see from the surface elevation profiles provided by ArcticDEM. This is another zoom in onto the ice cauldrons here along the edge of the ice cap. So you can see from these elevation profiles, you can see these topographic depression areas that actually represent the ice cauldrons. And also the lava flows that we mapped agree well with that from cancellations. Next example is for the 2011 Grimst Volcan eruption. This volcano is just south of the Byrd eruption that I showed just now. So it's just south of that. It's in the right center of this ice cap. And using the same technology, we can map the elevation change like here. You see a little bit of deposit thickness, elevation increase here, and elevation decrease here, probably caused by ice melting. This is a time series show. We have quite a few measurements like after the eruption, like several over the past 7 years. This slide shows you some profile along AA prime, and here is the black line again, shows the topography before the eruption, and the other colors shows the topography after the eruption. So you can see like before the eruption that there is a local high ground area here, and then the surface elevation decrease, and there is an increase of elevation around here. So this map shows a similar thing, like there is an increase of surface elevation probably caused by the deposits of the materials from the eruption. So again, this map gives you another picture, like looking at the elevation changes compared to the topography before the eruption. You can see there is a local topographic depression zone here, and then you got increase of the elevation here and decrease here. So you can see a lot of the various details, but still for this eruption, I don't see anything in the literature that show this similar thing. So we don't have this. So this data set is pretty new, and we need to more information to validate our results. The next example is the 2010 eruption of this volcano. Well, I tried to pronounce it, but I was like, oh, maybe I should better choose another volcano for my project, so it's kind of hard. I'm not gonna try it now. Anyhow, this volcano is very interesting because it has both eruptions around the summit area here, which is in center of the ice cap, and lava flows in the outside of the ice cap through a dike. So what we can easily measure is this lava flow here, because there's no ice coverage. And this is the time series of the surface elevation. So before the eruption, we have one spot DM, and after that, those are all ArcticDEM measurements. So you can see here, the blue shows the elevation increase, It means we have a lava flow about thickness of up to 60 meters. That's a very big number, and the uncertainty is about 7 meters or so here in this location. But in here, in the center, around the summit caldera area is very complex because during the eruption, we have debris flows and it's moving underneath the glacier and causing the melting of the ice, and the surface of the water flows away. Then we see a path of the lava flows after all the process. And then, but we don't know the bad topography before the eruption. So it's kind of hard to measure the lava flow thickness over here. But this result is pretty new, and I don't see any, it's very surprised that I don't find any other DEMs to mapping this. But a lot of data sets mapping, the DEMs are mapping the area over here. I guess they probably think it's very interesting here. Anyhow, I guess this should be the last example of the volcano eruptions that we've got too many. So this is the 2008 Arctic eruption. So I picked this one because there is kind of ongoing argument between some colleagues that are saying, oh, your DEM data is not, probably not suitable for this kind of eruption because due to the interaction between the magma and the water, this eruption, instead of producing lava, it produced a fine-grained tephra, which will erode away, washed away by water, rain or something. So that makes it harder to track the thickness that erupted from the volcano. But our data analysis shows that because we can, we have so many DEM measurements, we actually can estimate the trend of the elevation change rate, and that helps us to measure the elevation change during the eruption. So here the colored map, red shows the elevation increase. It shows clearly the new cone that's generated in this eruption. And the thickness is up to more than 200 meters high. And this profile shows, the black line shows the topography before the eruption, and the red line shows the topography after the eruption. So you can see all the interesting features. And this map shows the more interesting details about after the eruption, how the material is moving. Like along the flanks of the cone, you see erosion up to 15 meters per year, and redeposition in the center of the cone up to 6 meters per year, and at the bottom of the cone, you see about 1 meter per year of redeposition. So using this ArcticDEM data, we can see a lot of detailed information, and you can zoom in and to see the 2-meter resolution of details. So it's very cool. That's all for the volcanic eruptions, and then now I'm going to show some examples for the measuring landslides. So it's a similar process for in the data processing part, but the processing of the landslide is different. Like we have different kinds of landslides, like big landslides, slow-moving landslides, a landslide triggered by earthquakes, and thawing of permafrost. So first example I'm going to show is a new one. It's 2017 landslide in Alaska. This site is actually provided by our collaborator, Dr. Higman. Again, this map shows the elevation change. The background is a hillside of the DEM. Blue is elevation decrease. You don't see an elevation increase at bottom because the debris probably like flash out in the larger wide area, so you don't see much of deposits. So this along this AA prime here, You see, this is the top of the hill. Black line shows before the eruption, and the red line shows after the eruption. Sorry, landslide. I'm talking too much about the volcanoes. So, okay, you see these elevation decrease here, the drop of the elevation. This is the time series at the top here, the white circle here. And this time series shows you like how many DMs we get. Like we have like about 3 measurements before and 1 after, and you can measure the elevation change. It's about 35 meters per year. And then I was like, very interesting. You can see this subtle changes of the elevation like before the landslide. It actually could mean something, but I haven't investigated yet. But I think it's a very interesting way. Like maybe we could look at it. We can maybe see some signal like before the landslide. But what we found is that there is another very interesting landslide, like in Byrd Arm, that show exactly the same signal that I'm trying to look from here. This is a slow-moving landslide. It hasn't occurred yet, and we don't know when and whether it will occur, the landslide. So, but we're using the DM's difference. We can see the slow changes in the topography. You can see like elevation increase at the bottom here and elevation decrease. So it kind of represents a rotational landslides and how that reflected on the surface. And this is a very interesting example to show like the DM, not only we can map the landslide after the event, we can map the changes like before the event. And this is very important. It will help us like to model, to find those sites and to model that and provide information about future hazards. I think this is very important. In addition to that, we can analyze the mechanism, why does this landslide is moving. We see this landslide is right above this Byrd glacier, and this polylines shows you the front position of the glacier. You can see like between 2006 and 2020, this glacier is rapidly retreating. And then we mapped the front position of the glacier during the past 20 years, got the time series like this. And then we also mapped the horizontal motion of the landslides in the same time frame. You can see there is a strong correlation between those two. It means that there is supporting a theory called departuring because of the like before 2010. You can see from this image, the toe of the landslide is supporting by a thick, like 200 meters thick of glaciers. But then during this past 10 years, all that glacier melted away. So because of the loss of the support from the glacier, and then that could be a reason like why this slope is suddenly moving so fast. So yeah, using this data, we can understand a lot of processes associated with the natural hazards. Here's some error sources. First of all, we have blunders in the DMs caused by clouds, water, or shadows. And then, but the internal DM random error is really small, like 0.2 meters. In some areas we do, especially for the retrogressive thaw slumps that I didn't show here, we actually can get this sub-meter precision of the elevation change. So that's pretty cool. And then the co-registration error is the biggest error, could be several meters. And we also have to consider the impact of snow cover or vegetation on the height estimate. So it's a lot of things to consider for each specific example. Another challenge is like, as I showed in the algorithm development part, like you can use some filters to map out the actual landslide events, but there's still some challenges. Like for example, like you see here is probably a new slump, but here it could be an error. Like how do you, like when it comes to perfect mapping classification, it's kind of challenging. So maybe we'll consider some machine learning algorithms. We haven't studied on that part yet, like including the terrain slope aspect, those kind of different factors that may help us identify those events. Our first step is to carry out the change detection on a bunch of different sites that we already know from our collaborators. They provide field measurements so we can validate and compare our results, and then we're gonna try the machine learning algorithms to help identify those mass wasting events. So look at again the big picture. Our product will include the deposits from volcanic eruptions for this more than 20 volcano eruptions during the past 2 decades. And then a lot of the elevation change for the known landslides, so a lot of these sites. And then we're gonna provide an inventory of mass wasting events for the entire Arctic region. So in summary, ArcticDEM offer a great capability for measuring topographic changes at a large scale. And this definitely will help us improve the characterization and understanding of mass wasting events and natural hazards. Also, our final product, the mass wasting inventory, will provide firsthand measurements for analyzing the linkage between climate change and natural hazards. That's all. Thank you very much for your attention.
Thank you so much. I think we'll jump right into any questions that any attendees may have. If you want to submit any of those now. I see a couple that have come in. Chunli, can you see in the Q&A tab?
Yes.
Okay.
Now I see it.
Okay, or I can read them to you.
Okay, first question. Can you describe the methods for comparing XYZ change over time for landslides, like controlling for horizontal movement while measuring surface elevation change and error from co-registration? A very good question. Here, actually, we did the horizontal and vertical in a different process. For example, for this Byrd arm landslides, the vertical surface elevation change, we for the co-registration, we find those stable areas like over here and here that we know there won't be any elevation changes, and we do the DEM co-registration and get the DEM elevation changes. But we do a different process for the horizontal movement. We're using instead of using DEM, we didn't use DEM for the horizontal motion. We're actually using the original satellite imagery. From the imagery through the image feature tracking, we estimate the horizontal motion, and then similar process for the co-registration, like using stable areas like here and here along these slopes with rock surfaces instead of the glacier, the water, don't use any of those. And then we co-register the imagery, and then using the imagery feature tracking, we can estimate the horizontal motion along this within the landslide area. So it's a different process. They are not coupled together. I hope that answers your question first.
Thanks. We have another question.
Yeah, thanks. From Paul, yeah, is it possible with DEMs from lower resolution imagery? Is this possible with DEMs from lower resolution imagery? I'm not sure what you mean.
I think, if I can interject, I think maybe possibility of using planet imagery, and if there was any future possibility of using planet imagery to create DEMs, they're at lower, coarser resolution. Would those still be applicable for your research?
Yeah, sure. I think so. Like, it depends on your objective. Like, if you're looking at a large scale signal, yeah, absolutely, you can use. If you're looking at like 2-meter resolution signal, some of the slumps, the salt slumps are small, like 100-meter size in total. Like, if your resolution is too low, like 30 meters, then that won't be too much helpful. But if you're looking at a kilometer size of, like here, this landslide is about 2 kilometers wide, and then it's a relative sense. Your lower resolution DEM still can be useful, I think. I think the most important part is the quality of the DEM, the accuracy.
Great, thank you.
Yeah. Any other questions?
Doesn't look like it. Thank you so much. We really appreciate your work and collaboration with PGC, and really showcasing ArcticDEM and your work as well. It's really inspiring, I think, for a lot of folks to utilize this freely available data and answering questions that have been unanswered for, as you've mentioned, decades. So we look forward to seeing what you come up with in your future career as well. But thank you so much.
Thank you, Tiffany. That's very nice.
Yeah, and we'll be publishing this recording on our website, pgc.umn.edu, as well as on our YouTube channel. So thank you everyone for attending. Thank you for your time, Chunli, and hope you all have a great rest of your day. Thanks so much.
Thank you.